Hello and welcome to this episode of Mrs. Mulvey's Math Movies. In this episode, I am going to talk to you about choosing and using a geometric sequence formula, the continuous growth formula, or the doubling formula when you're looking at growth scenarios. So if you look at the whiteboard, I have two different scenarios here. On the left side, I've got a scenario where we're starting with 3,000 bacteria that we're culturing. And I tell you that the number of bacteria is increasing by 7% each hour. Notice that I'm not saying that the bacteria are growing continuously. I give you a rate at which the number of bacteria are increasing. And that's your key, that you are going to be looking at a geometric sequence. Over on this side, I tell you that we're starting with a colony of 3,000 bacteria, but I give you a doubling time. I also mention the growth factor. So for this one, because I tell you a doubling time, you can use the doubling formula. Because I mention the growth factor, and that's the continuous growth factor, you could also use the continuous growth formula. And we're going to take a look at that one in just a moment. But let's go back to this one. So if the only information that I provide to you is the fact of the increase rate, in this case the increase rate is 7% each hour, then you've got a geometric sequence. So this is the formula that you use to find the terms of a geometric sequence. But let's just take a look at this scenario. So we're starting with 3,000 bacteria. So the first term in this sequence is the number of bacteria at the start of the first hour. Then, at the start of the second hour, the number of bacteria have increased by 7%. So all of them were there, 100% of the bacteria, all 3,000 plus another 7%, which is 210. So really my common factor here is 1.07. Then I'd continue to multiply by 1.07 to get the next term. So you can see the start of the first hour, 3,000, started the second hour, 3,210, started the third hour, 3,435. And by the way, I did round this. It was a decimal, but I rounded. And I can continue like that, or I can use this formula that allows me to find the nth term of the sequence. And so I want to find the 8th term because that'll tell me how many bacteria there are at the start of the 8th hour. And it's equal to the first term times that common ratio to the n minus 1 power. And so I go to my calculator, put my values in, so I've got 3,000 times 1.07 to the, and then I can enter the 8 minus 1 in parentheses, but I'm going to do that subtraction in my head. I know that 8 minus 1 is 7 to the 7th power, and there's my answer. So if the bacteria are increasing by 7% each hour, we're talking about 4,817 bacteria. I'm not going to include the 0.34 because I can't have 34 hundredths of a bacteria. I either have one or I don't. And so I rounded, and when I rounded, that gets me approximately 4,817. So there will be approximately 4,817 bacteria at the start of the 8th hour. When I look at this scenario, where I have a colony of bacteria, again, it's starting with 3,000 bacteria. If you're told the doubling time, then you're going to use the doubling formula. If you're told that it's growing continually, or I give you the continuous growth factor, then you're going to use that formula. So I'm going to put each formula up here. And again, if you're given the doubling time, then you would use the doubling formula. You know it's the doubling formula because of the 2. If you're given the continuous growth factor, or you're told that it's continually growing, then you're going to use this continuous growth formula. If you're given a scenario like this where both are listed, then you can use either one because each one will get you the same answer, approximately. A little bit of rounding is involved with this growth factor, so it might be off by a bit. So you can use one or the other or both. And so in this scenario, to find that final amount, we are starting with 3,000 for each of these. That's the original amount. And then here we have the 2, and we're told that it's 7 hours later, so I put the 7 in for time. And I'm told that the doubling time is 30 minutes. Now I have to write that as a 0.5 because I wrote this in terms of hours, so this needs to be in terms of hours. And so when I take out my calculator and work on that, I get there it is, 3,000 times 2 to the 7 divided by 0.5 power. I get, let's see, yikes, 49,152,000. Over here, in this scenario, if instead we use the continuous growth formula, and I start with my 3,000, but now I have E, the K, this is this growth factor. So I've got the 1.3863. Hold on, my pen's acting up a bit. And that gets multiplied by the time, which is 7 hours. So if I entered that into my calculator, I'm going to get an answer that's close but slightly off because, again, this 1.3863 is actually a rounded value. And so here I get 49 million, oops, lost it, 153,940. So the answers are close, but again, there's a little bit of error introduced when I round this. And so that's why they're slightly off. If I would have used an exact and precise value for this, I would have also gotten the 49,152,000. So if it's presented to you this way, you can use either method. But if you're told the doubling time only, then you want to use the doubling formula. If you're told that it's continuous growth, or you're told the growth factor, then you want to use the continuous growth formula. If instead you're just told the change each hour, then you want to set it up as a geometric sequence. So that's it. Let me know if you have any questions about that. Bye-bye.